We are now moving into the last science session of GRIS 25. So we have the science session on applications and observations. And on the stage, we have Chair Gary Wick and Co-Chair Joanna Caragalli. So I will hand the floor over to Gary.
All right, well, thank you very much, Erica, and thanks everyone for making it back. Welcome to the session on applications and observations. We have 4 talks scheduled for this afternoon, and they look very interesting to me, so I say we just jump right in. So first up is going to be Daniele Ciani on surface currents, on his work on surface currents. So Daniele?
Thank you, Gary. Hello, everybody. So I'm going to present a study which has been discussed quite a lot in the last few years within the GRIS community, and is related to the improvement of the altimeter-derived surface currents using information from sea surface temperature data. For this meeting in particular, I will present some results on the North Atlantic Ocean, intercomparing the OSTIA level 4 near real-time and reprocessed SSTs. I'll go very quick here. Why ocean currents? So quickly going from your left to right, ocean currents are crucial to understand the ocean surface variability, air-sea interactions, but also lots of activities that also involve human activities at sea. One example for all presented here is ship routing. All these applications ideally would require a very high space and time resolution monitoring, although this is not recently achieved, considering the capabilities of the monitoring, especially from space, which currently is synoptic monitoring. So presently, we achieve a global scale monitoring at the operational level, relying on constellation of radar altimeters. So altimeters do sample the ocean topography along one-dimensional tracks. After that, we are able to interpolate this information in order to get two-dimensional gridded absolute dynamic topographies, from which we can derive the surface currents through the geostrophic balance. This actually generates some misfits, both in the representation of the absolute dynamic topography after optimal interpolation, so misrepresentation of the mesoscale features, but also the assumption of geostrophic balance is a limit, because the actual surface currents are not in geostrophic balance, but undergo other processes. Regarding the mapping, SWOT data will be very useful, especially in the characterization of the mesoscale features. But before ingesting these data, especially for past time series of altimetry data, we need to explore other methodologies to overcome issues like the ones you see presented here. So in 2 moorings in the Pacific and Atlantic Ocean, here you have in blue the time series of the eastward currents intensity, and in green you see what we achieve with the altimeter system. This is an example for the temporal variability, but spatial misfits can also be found very frequently. So SST is an ocean surface tracer that contains lots of information on the ocean dynamics. Here you see lots of meanders, eddies at mesoscale and submesoscale in the North Atlantic. You see superimposed the geostrophic surface currents, which are quite in agreement with the SST field, although the SST is somehow richer in terms of dynamical signatures. So we wish to extract dynamical information from this type of fields and bring it back into the altimeter estimates. Very briefly, the framework is dynamical, so we account for the SST evolution equation in order to get information on the surface currents. So starting from here, we wish to obtain a set of equations that, starting from the altimeter-derived surface currents as a background, so as a first guess of the surface circulation, we then compute some correction terms that are applied to the background field in order to get an optimized estimate of the surface circulation. And as you can see, the correction terms extensively rely on the computation of SST gradients and SST temporal variations, but also important, the knowledge of the source and sink terms of the CISSS temperature. Back in 2020, we performed an intercomparison study, intercomparing a few GHRSST level 4 SSTs. The outcomes of this study are briefly summarized here. We took into account the more ultra-high resolution SSTs, the REMS and the OSTIA. So the more were particularly good to describe fine-scale frontal features, although they were limited to prolonged cloud-free observations, so prolonged cloud-free conditions. The REMS merged microwave and infrared SSTs were quite good, particularly recommended for applications related to the equatorial and mid-latitude band. Some degradations in high latitudes were observed. And the OSTIA turned out to be the, let's say, the best trade-off for the global scale monitoring. We also had satisfying performances at equatorial band and mid-latitude areas, and a mitigation of the degradation found at high latitude with the REMS data. In the end, none of the considered level 4 SSTs gave an overall improvement at global scale. All of them had different characteristics. So the interesting point is also that applications like the one I'm presenting today can be considered somehow as an indirect tool of validation limited to ocean dynamic studies, of course. More recently, in the framework of the ESA-funded World Ocean Circulation Project, we derived a time series of ocean surface currents from the DUAX-18 version of altimeter-derived geostrophic velocities and the OSTIA level 4 sea surface temperature. And I also quickly wish to acknowledge the members of the GHRSST task team on level 4 intercomparison and climatologies for discussions related to this work. We briefly go on with some qualitative results. This shows basically the effects of the corrections brought by SST. What you can see is mainly rotation of the current vector, so a correction in direction and intensity in correspondence of very strong SST gradient areas, so along the main meanders and mesoscale eddies along the Gulf Stream, although this is very qualitative. Another interesting example is provided here and is extracted from the World Ocean Circulation Visualization tool. Here I emphasize in white the circulation prescribed by satellite altimetry in correspondence of a quite strong SST frontal features given in color. On the same date, we were quite lucky to find this drifting buoy flowing nearby. And in blue, you see the estimate of the WOC NATL to the surface currents dataset. So the correction brought by SST is quite effective. We lose this very strong cross-front circulation, which is quite unusual, especially for mesoscale geostrophic flows. Going on with more quantitative results, here I am presenting on a 3-year long period. On 2 degrees by 2 degrees boxes, the percentage of improvement of the surface currents after the correction with SST with respect to standard altimetry, using in-situ measured currents as a benchmark and relying on an improvement index, which is presented here. On top, you see the results based on the OSTIA near real-time level 4 SSTs, and below you see the corrections with the OSTIA reprocessed product. And the improvement brought by the reprocessed product is quite significant in this time period. So we went through a quite long series of visual inspections of the level 4 SSTs, comparing the near real-time and reprocessed product. This is a quite critical case. We saw it before in the animation. Actually, you can recognize these eddies and the meanders. This is a quite critical case in which you can see that the near real time gives a very smooth representation of the main dynamical features in the North Atlantic, while it seems much richer in the reprocessed product. If you compare the two level 4 SSTs, you get to differences of about 10 degrees, mainly due to a shift in the representation of the main mesoscale features. Other examples, which are much more in agreement, at least from a first visual inspection on May 2019, 21, sorry. Still, you can get to differences by about 5 degrees, and particularly along the axis of the Gulf Stream. So again, potentially mostly a shift in the representation of the main mesoscale features. We went even further. We wanted to characterize quite a bit the spatial and temporal content of the OSTIA near real-time and reprocessed product, extracted information useful for our application. Here, I present the temporal variability. So as a difference of the temporal standard deviation between the two level 4 SSTs, and you can recognize a much larger signal in correspondence of an active dynamical area, again, at the axis of the Gulf Stream, with differences by about 1K here in this area. And again, focusing on this sub area here, we performed a spectral analysis. The results are presented here. In red, you see the spectrum, power spectral density of the reprocessed product, which in the, let's say, large to small mesoscale range indicates a more efficient representation of the spatial features. So these are the results for the 10 years long reconstruction in terms of improvement of the altimeter-derived surface currents. So we basically got improvement in the majority of the basin, almost no degradation or very light degradations. This is, again, very visible along the axis of the Gulf Stream, where the SST gradients are generally larger. Interestingly, we also got some significant improvement in upwelling areas, although some alternating degradation boxes are present. You can find more details in the websites presented here. So a paper describing this methodology, the link to the Ocean Virtual Laboratory to visualize many interesting study cases in which you can also superimpose different layers and visualize the synergy between different observations. The dataset is freely accessible through the WOC portal, and this dataset is also part of another algorithm that estimates the three-dimensional currents, including the vertical component in the North Atlantic, and on the same time period, 2010 to 2019. So concluding very briefly, we presented this new dataset for ocean dynamics applications that demonstrated that SST can indeed be very useful to improve the estimate of the ocean surface circulation. We got improvements up to 15% on a 10 years long time span. And of course, these improvements are more effective in strong SST gradient areas. So along the Gulf Stream, for our case, we basically go back to altimetry in other areas. And regarding this reprocessing of past time altimeter data, we recommend to go for the OSTIA level 4 reprocessed SSTs. So I'll stop here. Thank you so much. Taking questions.
All right. Thank you very much, Daniele. Questions? Yes.
Yeah, I think for the data similar to ocean models, they do assimilate both our temperature data and SST data for Galbraith or HiCom. How do your products compare with these data similar to ocean models? It's consistent or not?
We didn't check. I saw a poster actually on assimilation of SST and altimetry data in one of the previous sessions today, and it seems that including sea surface temperature is always beneficial for the model performances. But we actually did not intercompare our surface currents with the outputs of a numerical model, including data simulation. this is something we could double check. Always using in situ measurements as a benchmark, of course.
Okay, thank you.
Thank you.
I enjoyed your talk. This looks really exciting. My question, in addition to the validation with the model runs from the previous question, have you tried working with someone who has like detailed currents, like in the California current regime, where you can actually compare it to a detailed suite of observations?
We didn't for the moment. It's a suggestion I'm certainly going to take for future applications, and we can discuss anytime, Shakila. Thank you.
All right, I see Marwan online has a question. Marwan, go ahead.
Hi, Daniele. This is Marwan from ORBTI. Could you replace SST with another tracer, like chlorophyll concentration, and use the same method?
We made this attempt in the past in the framework of another ESA project. We tackled the ocean currents reconstruction in the Mediterranean area. For this type of studies, we went through two phases. First phase was an observing system simulation experiment in which we synthesized altimeter-derived surface currents from a model sea surface height, and also mimicked the ocean surface chlorophyll concentration derived from satellites. At the observing system simulation experiment level, results were extremely promising. When switching to satellite-derived data, we found several artifacts, at least in the level 4 surface chlorophyll concentration in the Mediterranean area, which, as I think you saw briefly in the methodology, are the main source of the correction of the background circulation. So yes, we tried with slightly less satisfying results. I also have to say that the Mediterranean is quite challenging for this type of application. So we should maybe go back to other areas as the Atlantic. But I'm wondering about cloud cover issues, which could impact the consistencies of the gradient for dynamical purposes.
Thank you.
Thank you.
All right, I see Jorge has a question.
Thank you, Gary. Great presentation. This is so exciting. I just wanted to ask you, with respect to applying the methodology to other areas, for example, SWAT off the California coast, where there's so much sub-mesoscale. Do you foresee that as something possible in the future too? You know, for looking at, you know, these kind of issues and applying SST and.
I hope in the future we will be able to explore further this methodology, even using SWOT data. It is likely we will be working on that, still focusing on the North Atlantic, but I think that switching to other areas can be very interesting, yeah. And using SWOT data would not be that trivial. But yeah, we have some ideas in mind on how to extract information from those data for this type of methodologies or other methodologies that makes extensive use of machine learning.
Okay, thank you so much.
Thank you.
Because the SWOT data also right now have these cross-track biases and everything. So what I think,
exactly,
once some of these things are calibrated well, this could be. Anyway, thank you. Great presentation.
Thank you, Jorge.
Any quick last question right now? All right, thank you very much. Very nice.
Thank you all.
All right. Okay, next up we have Peter Galbraith talking about product selection, calibration, and coverage. So please take it away.
Thank you. So I guess it's really a user presentation. I'm not part of the community. So basically I run a monitoring program in Eastern Canada. We're basically called the AZMP, the Atlantic Zone Monitoring Program. I myself report on the physical oceanography of the Gulf St. Lawrence for sea ice water column, which includes the SST, and I also help my colleagues from the zone producing the SST products that I'm showing you today, as well as the sea ice. And so sort of an example of what we we show. So if you're going to set up a monitoring program, what are your criteria to use SST as a user? Well, we need a 30-year climatology, basically, because we're going to set anomalies based on a standard 30 years. It doesn't need to come from a single data set. We can merge them as long as we are sure that they cross-fit, right? No filtering out of cold anomalies due to mixing and regional upwelling, recurrent upwelling spots. And this will come up a little bit later. Of course, real-time availability, like next day, another issue here. And we need to resolve half a standard deviation because we usually report on this sort of color palette. And everything within half a standard deviation of intraannual variability will be near normal. So pandas white and anything warmer red, so forth. So of course, at the pixel level, this is really easy. But it's when you go to ensemble averaging that you get more errors and stuff. So we'll come into this later. So the 30-year climatology we have, before your group existed, probably we had this internal product which covered all of Canadian waters. And it unfortunately stopped being produced in 2013. And by then, another DFO, Fisheries and Oceans Institute in Halifax, was producing their own SST lab. They were producing a product. And so I started blending them together. And by sheer luck, basically published the blend in 2021. And a year later, someone retired and they stopped making it. So we went on a hunt for something new. And this is where your community comes up. And everyone was telling me use mur, which in French we say mur. So anyway, but mur has a problem for us. And this question of filtering out cold spots. And for example, off of Yarmouth, the head of the Laurentian Channel, and here, recurring upwelling or mixing, tidal mixing, which tend to be washed out in mur. So of course, if I'm blending mur with our standard climatology, this would always show up as hotspots, which we don't want. But the Star Leo product was one of the ones that we tried out, and it seemed to be less affected by this. And this is early, one of the early years. This product starts in 2007, and it looks a little bit washed out, but better. And in its later years, it's I don't know why, but it's much better. So this is the BIO product for one given day, and this is the L3S Leo Star product. So, and it also includes more satellites, so we get more coverage. So we elected to go with that product. I didn't test all of the 142 of the catalog, sorry. So, selected Leo, so it has one daytime, one nighttime file, which we download every day, and we make our own daily. If we have at each pixel both values, we'll just average them. And if we have one of them, we'll just subtract half the mean value basically over the many years of time series that we have. But soon now we have everything working, but they just introduced, working too fast for us, a new daily product, which will take that step out of the equation. And it goes 7 years further back in time. So we'll be happy to try that out and to insert into our chain. So we need to calibrate Leo to our own data. Basically, it's self-consistent, but maybe not consistent with what we're using. So we want to make sure that we ground truth it to our own data sets. And to do that, we have a series of oceanographic buoys, basically, that have sort of like MET buoys, but they also have CTD profilers that measure into the water column on them. And we have a thermograph network, which I'll show on the next page. So in total, over the overlapping years, I had over 10,000 days of overlapping data at these sampling sites with a Leo pixel. So not millions like I saw in other presentations, but it's still like 28 years of data at a single point. So for us, it's pretty good. I threw out about a third of the data where the diurnal range was very high, just to try to drop down the fit a little bit more. So these are basically our buoys at these locations. And we also have thermographs deployed at each of these sites, and I'm only using the offshore sites. These are thermistors deployed on Coast Guard navigation buoys. So they get deployed by, we just put the sensors on the buoys, and Coast Guard deploys them for us, and we recover them. So it's not real-time data, but I had years of these, right? And this is the calibration. So we have thermograph versus satellite, and the lines for the thermographs are the diurnal variations of 1 day, putting a line. And when it's a white line, it overlaps the satellite measurement for the day is within that range. And if it's black, it's the satellite observation was outside of that range. So if we just did a linear regression, we found that Leo is from 0.2 degrees at 0 to 0.4 degrees at 20, a little bit too warm. So we just corrected that, actually the reverse, 0.4 at 0 and 0.2. So we just corrected for that. And once corrected, 95% of the satellite data fell within the diurnal range of our observations. So we're quite happy to be using that and insert that with our old data, which was compared in a similar way, and know that they will fit. So then we make our own weekly and monthly composites, and no news to anyone in this room, but maybe some users aren't aware that you don't just average all pixels, see temperature pixels, because then you'd have problems with spatial gradients and temporal gradients. So what we do is we take, for this week, we take all the daily composites. We have the daily climatologies for each, and we just subtract, so we get for each day an anomaly. So we do the mean anomaly, and we add that to the climatology for a week, and we get our best shot at what the week SST is for that week. If we want to do a box average on an area, we could do the box average of this picture, but we actually don't. We actually do sort of the sum, the average of all available anomalies for that box, and we add that to the average of all pixel climatologies for all of the days. This is the equivalent to basically weighting each of these pixel anomalies by the pixel count for the week. So that gives us a number as like the best temperature we had, the best temperature that we could have for the area average. Now, if I go back to this slide, you'll see that a few of these days have very few sparse data. So how much data do we actually need? This is shown here. So these are the boxes that we reported on, the polygons. And overall, all the years, I had 109 months where one of these boxes had more than 50% coverage. That means that for every day, all the possible pixel combinations I had more than 50%. So this is the best that I can get. It went up to like 64%, something like that. So then I want to simulate what would happen to my estimate of temperature if I remove some of this to degrade my pixel count. And how I do this is I have 30 days of data, and I first take out 1 day, each of the days, and I compute a new estimate of the SST. And then I remove 2 days randomly, do that 30 times, and so on to 30. So it's like a Monte Carlo type of thing. So I degrade the data voluntarily, knowing what the perfect result should be. And like take the bottom row here, the Gulf St. Lawrence box, start off at like 64, and I've scaled this error, this uncertainty to half my standard deviation, which is my goal, right? So anything below 1 is good. So as I degrade my percentage of pixel availability, the error goes up, creeps up. And at 40%, the blue line shows the 95 percentile of all my Monte Carlo tries. So even at 40%, 95% I'm going to be right. And degrading further, I see that even at 7%, I'm right. The red line is the median of all my Monte Carlo tries. So even at 7%, I'm going to be right half the time, which is not bad. So you don't really need that much SST coverage to get a good answer. What do we do? What do we report? Well, as I showed at the beginning, I typically show line graphs of weekly data, and these will be indicated as anomalies in this top row of little boxes. Then I'll show monthly anomalies with records here, and you can see the massive heat wave in the estuary here, where water in the late fall was as warm as expected in this blue climatology shown here. So this was like 20 media interviews just for this one thing, right? And this panel shows percent coverage that we get over all of these boxes for the last 2 years. And you can see that in the summer, we tend to be above 50%. We're doing pretty good. So this gives us a good idea of the certainty of the reliability of what we're reporting on, which is kind of important when you do state of the ocean reporting. This plot shows for all the regions the mean SST for that we've computed based on the available pixels and their anomalies for each box and anomalies. And anything that has a highlighted white outline is a record for the month. And you can see that across the zone last July, the marine heat wave that affected the whole Northwest Atlantic got all of our boxes at record high for the month. And we had another marine heat wave in the Gulf St. Lawrence in the fall that I showed you here earlier. We also report on seasonal averages, which will vary from year-round to less than year-round up here, where there's lots of sea ice. So we'll do that. And to get like one number for the zone, we'll do a weighted average by area of all these numbers to do a stack of the stack bars, basically a stack of the all of the anomalies to get just one number. You can see the last 3 years have been really, really warm and off the record, off the chart records for the Atlantic zone. Where do we report? Each year we publish regional reports for the Gulf St. Lawrence, the Newfoundland Labrador Shelf, and Scotian Shelf. And we also merge this into a summary report for the whole Atlantic zone, which also includes the biology from ocean acidification to nutrients up to zooplankton. And we feed into national state reporting reports and internationally to the ICESSS report on ocean climate and to the North Atlantic Fisheries Organization, NAFO, into their sort of reports. Just to end, a few quick fun things that we tend to do. We got science results, basically. So this is for the Gulf St. Lawrence. The black line shows the weekly 30-year climatology from this blend of different products. And the gray line shows 13 stations from Environment Canada that are also blended together. And you can see early in the season that air temperature is warmer than ocean temperature, so it's warming it, and in the fall it's cooling it. But if you offset them by 2 weeks, they fit perfectly. So this is a nice climate change tool showing that the coupling is so strong that air temperature is a good indicator of what the SST is going to do. So, but more than this is a 30-year climatology, but the area under this curve for SST is basically the mean temperature between May and November. So interannually, this curve goes up and down, right? And this shown here, this is the May and November average of the satellite record for the Gulf St. Lawrence. And we can see the last 3 years are really high. And we overlay that with the interannual air temperature, and we recover 72% of the variance, meaning that we can use air temperature as a proxy for the Gulf St. Lawrence for SST and go back 150 years and get a warming trend and so forth. So that's all I have. Thank you.
All right. Thank you very much, Peter.
Ran a little
Question?
long. Maybe there's no time for questions.
No, I'm going to kind of mix.
Okay.
I'm going to roll in some questions as we go. So please, questions for Peter.
Oh, yes, we do need remote sensing. We just need, and don't go overboard filtering stuff out. It might actually be valuable, because if you over filter, we can't use it. Is sort of the message one of the messages that I want to give today. And also give us the longest possible, go back in time if you can. It makes it easier for us to establish long climatologies without blending too many things together. Not everyone is as careful as I was to blend things together. A lot of people will just take 2 data sets and put them together and mash them up.
Okay, we've got Ole online with a question. Ole, go ahead.
Hey, my name is Ole Jonas, and I'm the lead developer on the L3S LEO SST. So I'm from the NOAA-SISST team. So I'm really glad you were able to use our data, first of all. And you also mentioned that you said that the data got much better later on. So that's quite simple. It's just because there's more satellites. Like in 2009, when you were looking at the L3S AM, it was just MATLAB A. There's nothing else. But if you look at after 2012, then you had MATLAB B, and then after 2018, you also have MATLAB C if you're looking at the AM product. So it's a simple reason. It's just more satellites in later dates.
Yeah, well, this was more in terms of masking cold spots. It seemed to get better later in time. Even when we had a pass over a cold spot, it tended to be a little. You could see actual pixels getting masked out as you went into the cold spot.
But if you have more satellites, you're more likely to get a nadir pass, where you can be more. You could be more. You don't have to be so careful in the cloud mask. Like you're more liberal in the masking when you get a near nadir pass. So with more satellites, you're more likely to get one of those. So you're more likely to catch these cold spots without masking.
Thank you very much for your products. We're very happy to use them.
But yeah, so you should probably mention we now have updates since you downloaded that data. So now we have added MODIS. So that's why you're able to get back to 2000. So hopefully you will be able to take a look at that.
Okay. Any last question? Really? All right. Excellent. Thank you very much. All right.
Really
Appreciate
to hear them from here.
It is. It is. All right. Next up, we have Andy Harris to talk about some work on diurnal warming. So, Andy, to you.
Yeah, I guess this is the kind of like the mixed bag science session where people couldn't, nothing fitted anywhere else. So, so we're moving to diurnal warming, which is like much more of a process kind of thing rather than looking at actual satellite data itself. This is work that I've been doing with Gary and Sandra. We did actually get some funding to do this, which is great. And we did get some way towards, we had a lot of ambitions for the project, but did I actually touch this? Wow. Anyway, let's say we could. So the main motivation behind it is being, if you're going to combine data from different sources that happen particularly at different times of day, you're going to have to account for the diurnal warming itself to be able to put these things on the same level playing field before you assimilate them into the analysis. And so that's the kind of a quick overview of the actual geopolar blended analysis system. We did have a diurnal correction, which we put in there. That's been in there for a few years. And we actually have a, that's the block of extra stuff. I did not touch that at all. What's going on? So let's just wind that back a little. So we're putting extra information in there, which includes NSAP fluxes of heat and momentum, and then estimating diurnal warming on a global grid, and then extracting the information for a given time of day and applying that adjustment to individual satellite pixels as we ingest them into the superorb before we perform the analysis. And the model we're using is basically one that's been continuously evolving, I would say, well, relatively discontinuously evolving. Maybe it's a diffusion scheme, so it's basically turbulence closure, and it's the current iteration has 100 and something levels in the model, and we have so it could be regarded as a fairly, it's close to the state of the art. You've got simple parameterizations, you've got bulk mixing schemes, which have sort of instantaneous mixing, and then diffusion schemes like this. And so we can simulate the full profile of heating throughout the day. This is a kind of idealized example you're looking at here. As you can see, the time of day and the growth of the diurnal layer, and then it kind of erodes as we get past the peak of heating. And it just so happens that that's what it looks like. It looks great. This is something, I think I probably first showed this maybe in South Africa. That shows you how long ago it is. So it looks great. Okay, but at first blush, but basically there's actually rather a lot of warming, maybe a little bit too much warming in the tropics in particular, which we weren't particularly happy with. And it occurred to me that maybe we should be looking at trying to adjust things. One of the things, of course, with turbulence mixing schemes is that the state of the art, but there's a lot of tweaking that you can do. Semi-empirical constants, probably the main one is the background mixing term, which is essentially when there's enough buoyancy production to inhibit the vertical component of turbulent eddies, you basically default to some background mixing that you specify, which can vary by a lot, 2.5 orders of magnitude roughly in this scheme. You can tune these things and they can work really well if you've got really good fluxes going in. But we need it to work on a global scale with numerical weather prediction fluxes. And as I said, particularly, we were concerned about the amount of warming in the tropics in particular. And it occurred to me a while back that there was something missing, and that's in the primary heat source term. In other words, the insulation scheme itself. And that is we didn't have any dependence at all on water vapor. And because it's pretty well known that the near-infrared parts of the solar spectrum are strongly absorbed in the atmosphere by water vapor, we should probably build something like that in. And also these near-infrared terms, they're the ones that get absorbed very close to the surface. So they're the ones that are really producing the strong buoyancy gradients near the surface. And so did some calculations with ModTran, took a global sample of atmospheres, took some varying solar zenith angles, and computed the change in the insolation in 9 bands. This is the well-known Paulson and Simpson 9-band scheme. The varying solar zenith angle also dealt with the change in the dry air absorption that we observed. And that also keeping it with that 9-band scheme, and everything else was kind of relatively, compatible with what we had before. But our initial results gave us pause. And when we thought, well, let's have a look at what's going on in the in-water absorption in the scheme, because really the first thing was just dealing with the Planck weighting in the atmosphere. And so we looked again at that, and Paulson and Simpson refers back to Albert Defant's book, which is a 1960 book. And there's a table in there that refers to Schmidt 1908, which at that point it was like, it's time to look at this again. So we took the Segelstein 1981 pure water, high resolution in water absorption, convolve that with the ModTran spectra, and then map that back into the 9 wavelength bins. And we did get some significant changes in one band, and the water vapor dependence is also there's some change there. And we also thought, well, we ought to be, while we're at it, put some refraction in. So we put a very simple refraction in. So the 1/E depths are scaled by the cosine of the incident refracted ray. So what the question is, so next thing is, having done that, of course, we had a tuned model that worked well with cruise fluxes and things like that. Gary is very happy with the way it behaved. Now, when we applied the new scheme, what we found is that we ended up decreasing the diurnal warming. So instead of being up here, it's kind of came back down by about 1 degree. And so we essentially ended up having to revise the tuning on the model to get it back up to the original amount of diurnal warming thereabouts. And the end result of that is here we have original warming Our original warming is here. New warming is somewhat reduced, particularly in the tropics, and this is the difference plot, essentially. What you're looking at here, by the way, is the 90th percentile of the peak warming for any particular month. And when I say any particular month, in this case, it's July. And this is done with respect to a set of static coefficients where we basically kept it at 48 degrees instead of allowing it to vary. So we kept the mean water vapor amount and the 48 degree solar zenith angle. And so you can see a bit of a depression in water vapor in the tropics, and then you get a bit of an enhancement in warming, which is basically the effect of the solar zenith angle change. But then, of course, that is July. What does it look like when you go to a month where the sun is directly overhead? Well, unsurprisingly, overhead of the tropics, that is, unsurprisingly, the effect is much greater for the water vapor in the tropics. There's really quite a significant change. And you still also get that higher latitude enhancement due to the solar zenith angle. So it looks great, well, great-ish, or at least something we ought to be doing. The question is, how does it validate? And so this is a look at using geostationary data to do the validation. And you end up with, this is stuff that has been, I guess, 2020, is it? Oh, actually, let's say so there. Okay. So this is something that Gary and Sandra particularly have been specializing in, because obviously diurnal warming, observing it with geostationary sensors makes a lot of sense, basically, because you get a nice sample around the diurnal cycle. Now, basically, the data are kind of filtered so that you have to have a sort of a continuous record, or almost continuous record, over 24 hours in order to pull out what would you consider a reliable diurnal cycle. So this is an example of sort of one day that you can pull out. And also another thing here, what we're looking at is a comparison between, we do also have an overlap, basically. So here we have GO16 diurnal warming, and you can overlap it with Metersat 11, and on the right-hand side, what we have here is the comparison between the several observed amplitudes going up to, 4.5 degrees here, or at least they're going a little higher, really, going up to maybe 4.5 degrees in the GOES data. Oh, no, that is something else. Put it back. Okay. But another thing you can see also is that for the warming here, generally speaking, it is maybe a little bit warmer in the GOES than it is in the Severy. And I think that's simply due to the fact that the GOES is maybe a little bit more sensitive, more closer to one-to-one responsive algorithm. So it sees a bit more diurnal warming than the Severy data. And now we have illustrations for Himawari 8 and GOES 16 for the July case and the March case. Now, they're not perfect, obviously, but they do kind of line the one-to-one line. Anyone who's done diurnal warming modeling and tried to get it to match with satellite data, essentially, we're used to having this something close to a cloud of points, but actually we are quite happy with the behavior, I would say, in all of these, apart from possibly there's a little bit of a truncation. Oops, I do not like this pointer. But you can see that it's working pretty well now. Now, one of the ways to get around the fact that when you're trying to do these point-to-point comparisons, you're heavily dependent on having accurate fluxes, is instead of looking at the individual points, is you take a look at the distributions, and these are logarithmic plots. And what we have is the satellite observed diurnal warmings, and the static model is the red line, and the full 2D new scheme is the green line. And so here we would say that is generally closer to the black line. So we're pretty much happy that that is better. And again, here we'd say for the majority of this, that is better. We're not particularly happy with this March case. They're both not very good at the higher warmings. We're sort of losing a bit of warming here. But again, over in March 2020, again, I would say that generally speaking, we're happier with the green line. So overall, we say it was an improvement. There are plenty of remaining questions, though. We had a very ambitious project, probably did about half of what we wanted to do. one of the things we want to do is we want to look at the effect of cloud, because we're making an assumption of clear sky, and if you put in something like a water cloud to inhibit a little bit of your rate, obviously it's completely cloudy, you get almost no solar flux and you get no diurnal warming. So the 100% case isn't really an issue, but the ones where you've got a little bit of broken cloud in there, essentially if it's water cloud is more absorbing in the infrared, and so what you'll find is that you will greatly affect the distribution of heat. So much more radiation penetrates per unit in incident radiation when you have water cloud, like say low stratus. If it's ice cloud like cirrus, it does penetrate a bit more, but it's nowhere near as dramatic as it is for the water cloud. And then we have, this is the clear sky case that we had before. So other things that we obviously wanted to do, unfortunately, the model is still hanging on to its warming a little bit too long after the peak. That we haven't really figured out exactly what's behind that yet. That's something we desperately want to try and figure out. And obviously, ocean biology, there's been quite a lot of work on that, which is essentially, that's an in-water absorption term as well. And of course, what we're talking about here overall, what I've been talking about is the heat source term into the model. So after the first thing you do is dump some heat into the model, and then you do turbulence and mix it around. If you get the amount of heat you're putting into the model in the various layers wrong, then anything else you're doing to tune it is essentially trying to correct for an initial error. So we need to get this thing right first. And so so what I've presented thus far is something we really ought to be doing, which is to put in water vapor and solar zenith angle. And then these are the other things that we really ought to be doing as well. Now, to summarize, I think we basically essentially addressed something where we had a problem, which was like too much diurnal warming in the tropics, and particularly putting in the water vapor does dampen it down, particularly depending on the season. And then, of course, it does enhance the warming at higher latitudes as well, which is kind of useful. So overall, the balance is significantly better. But we want to put cloud in the sim. We want to put ocean biology into the system. Those 9 bands that we talked about, it's very useful for the point of view of ocean biology, because quite a lot of work has been done using bands like that, but there's probably an even better way of doing it, which probably involves doing some principal component analysis to get you a better optimal distribution of in-water absorption channels. And by the way, for what it's worth, this is the mean diurnal warming change with and without the scheme changing, because before we had the 90th percentile, so that shows you the effect. I do not like this pointer. And the revised model has been already ported. Gary went over, and we're all 3 of us over there in June of last year working on different aspects. Gary's working on the model, and the hooks are in there for this new insulation scheme with the water vapor. I submitted a paper to GRL February time. It's still in review. Gary submitted a paper to Earth and Space Science, and that's already come back with minor revisions, so that's nice. So yeah, hopefully there'll be some good news report. I mean, I did check this morning, it's still in review. We seem to be on the 4th reviewer now, which is a bit alarming. So anyway, and that's all I have for now. Thanks.
Thank you, Andy. Questions for Andy?
Since you have the time series of GOES cloudiness over the course of the day, you could do something like watt hours up to the point of the particular retrieval as a way of kind of looking at the dynamics of the heat flux into the surface of the water layers, and that might give you the adjustment that you're looking for.
I mean, I know what you're saying. Basically, you're saying for example, there is an insulation product that is provided on, or maybe a 1/10 of a degree grid, something like that. So it might be useful. I mean, the main thing for us is really to be able to filter the insolation by a kind of cloud fraction, really. So if we have separation of the cloud types, which generally do in NWP at least, we're initially trying to get it to run off NWP, so we don't really have, we don't have the geostationary cloud and installation information everywhere. But yes, we could do a study like that if we were fully confident of being able to identify all the cloud types and so on and so forth. So we could do something like that and include that in the next stage as well, yeah.
Other questions for Andy? Checking online, yeah.
Andy, this is a simple question. Is there any kind of interaction between this diurnal cycle and the mixed layer depth change?
I mean, you'd think so. I mean, obviously, the main thing, if you get a very large diurnal cycle, then that means there's not much wind mixing. So it may be a slightly more complex answer than you might think, because if you had a lot of wind, but you also had clear sky, I suggest that that's more likely to produce a deeper mixed layer than if you have not very much wind and clear sky. Of course, clear sky tends to go along with subtropical high pressure ridges and stuff, so there's not much wind anyway, so there's a bit of a correlation, but it's not so straightforward, because if you have a lot of diurnal warming at the top, that means you'll have a lot more heat loss from that top layer at night, and a lot of it will escape back into the atmosphere before it has a chance to get mixed down.
Any last question? All right. Thank you, Andy.
Right.
All right. Our final speaker of the session will be Sandra Castro, talking about some cool skin effects.
I just want to get familiar with the infamous clicker before. Okay, what do I do? Okay, as the title of this presentation suggests, I'm just going to show you some examples of measurements of the cool skin that we obtained or we've seen popping up more often lately that are not in agreement with predictions from delta T from parameterized dependencies based on the wind speed alone. This is work I've done with Andy Jessup at the University of Washington, Gary Wick at NOAA-PSL. And I want to say thanks to Anne, Igor, and Gary, because this work really got started last summer as an invitation to visit them as UMETSAT, as part of the UMETSAT Visiting Scientist Program. So I'm going to give a very brief introduction to the cool skin, because this is one of the main foci of this talk. This was an area of research that was really active about 25 years ago. Then it sort of went fall out of fashion, and recently it's raising some new interest within, especially the gas transfer community. So here we have an illustration of nighttime SST profile, temperature profile at the surface of the ocean. And under normal conditions, when you get heat loss out of the ocean, you see this cooling of about 0.2 of a degree over across a really thin layer of about 1 millimeter thick at the ocean interface. This is what we call the cool skin, and we're interested in evaluating the difference between the skin SST and the sub-skin SST. This is what I'm going to refer to as just delta T. So the skin SST we can obtain from infrared radiometers, and for the subskin, we take advantage of the fact that the profile is isothermal below the cool skin, so we can use measurements from different depths to approximate the subskin. In past theoretical work, these delta T was observed or determined to be a function of both the heat flux and the wind stress. But given the lack of reliable heat flux measurements, we had to go around, and this delta T was simplified even further, and it was assumed to be a function of the wind speed alone. So the measurements I'm going to show are sort of challenging these wind speed dependence only. So I'm going to take a quick look at the simplified parameterizations that I called Donlon type dependencies. Okay. So these Donlon type simplified parameterizations are based on the nighttime dependence of the delta T on wind speed. And as you can see here, when the winds get high, the delta T becomes nearly independent of the wind speed, and only a very small but very constant temperature difference remain at the interface. So the delta T, Donald was the very first one that evaluated these sort of constant of proportionality at high winds. This is his 1999 data for the Atlantic. And from this negative exponential, he determined that for winds greater than 6 meters per second, the mean delta T approaches a cool bias of minus 14 tenths of a Kelvin. These sort of studies have been repeated in multiple regions of the ocean, all of them with very similar parameterizations. They're basically the same negative exponential with these asymptote at high winds just varying within 2 millikelvin. In the 2002 paper, Donlon and co-authors just took a bunch of these regional dependencies, they averaged them, and they came up with these revised cool bias that is more representative of the globes of the ocean globally. These cool bias became sort of the cool offset used in satellite validation. And it's pretty easy because you can take a bunch of subsurface temperatures from buoys, filter them for wind speed, add the cool bias, and you get large numbers of skin temperatures that you could use for skin validation. All of these results, the winds, if they get high winds, they're not larger than 15 meters per second, but it's assumed that this constant value is valid for all wind speed. So any deviations from these asymptote are assumed to be errors in the skin retrieval. So what we are proposing here is that they're not skin retrieval errors, but they're actually physical. So I'm going to show new data sets. Three of them are based entirely on cruise data, and the fourth is a hybrid data set that uses skin SST from satellites, buoy data for the subsurface temperatures, and reanalysis winds and heat fluxes. So let's look at the very first data set. This comes from SMODE. SMODE is a NASA campaign. It's ongoing, but the very first phase of this experiment took place in October of 2022, and the purpose was to look at the physics of submesoscale fronts. So they picked these, this front off of San Francisco Bay, and for the space of 3 weeks, they just went back and forth with different instruments. The data I'm showing here was provided by Andy Jessup. He had a Rother radiometer on the bolt horizon, and the subsurface temperature came from a snake, which is a precision trailing thermistor that measures SSTs at a depth of 5 meters per second, roughly. This is the time series of the Rother skin SSTs for over 2 weeks, and you can see that the radiometer was able to see the frontal passing pretty well, the magnitude from from one side of the front to the other was about 4 Kelvin, and the front was pretty stable for about almost 3 weeks. If we look at 2 of those crossings, and here on the left we have the cruise track and color-coded by the skin radiometer, but I want you to see the top one, and we see that the skin and the bulk just very in unison as we cross the front, and for those 2 passes, the delta T varies between 0.2 and 0.3 degrees Celsius. But the wind speed is very, very constant. You can see it in the wind vectors or here in the time series of wind speeds. So that means that in this particular experiment, the delta T was being driven not by the wind speed, but by the heat fluxes. So I'm going to show this plot many times. So this, let me guide you what it means. These are scatter plots of delta T versus wind speed. The red curve here is the Donlon simplified parameterization based on the wind speed only. The error bar plots are delta T, observed delta T bend in 1 meter per second wind bends. So what we're gonna try to show you is areas or conditions where the observed dependence disagree with the red curve. So in this particular experiment, they couldn't be more different, the observations and the Donlon dependence. So as you can see, for low winds and low heat fluxes, essentially there's no dependence between the wind, the delta T and the wind. Only when the winds increase by 6 meters per second, we see an increase in the cool skin with increasing winds. And only for winds greater than 12 meters per second, they sort of converge. The other interesting stuff here is that for the higher wind speeds, we start to see some stratification of delta T on heat flux. The next example uses data from ISMAR from the 2016 to 2018 investigator cruises. These are around Australia in the Southern Ocean, and I extracted the data from the threads catalog, the ISMAR thread catalog, but this data has been published and it has been shown before in this during GHRSST. Sang derived his own parameterization, simplified parameterization in 2020. And as we can see for the nighttime dependence, the observations follow pretty well Sang's dependence up to 10 meters per second. But after 10 meters per second, the observations deviate from the Donlon asymptote. So we have increasing delta T's for increasing winds for winds greater than 10. What is very unique about this data set is that you can see a perfect stratification of delta T with wind speed basically for all winds. It's hard to see these in other data sets so cleanly. The third data set is from EPIC. This was a NOAA campaign that took place in October 2001 off the Bay of Tehuantepec. And the data, the SSTs were provided by Andy. He had a Serums radiometer on board the Brown. The snake, the subskin SST comes from the snake again. And the fluxes were provided by Chris Farrow at NOAA PSL. Here we see also that the observed dependence sort of tracks downline. It has the same tendency, but there's a constant offset of about 2/10 of a Kelvin. And the other interesting stuff is this departure for winds greater than 10 meters per second, and they're driven by very high heat fluxes. Finally, we have the hybrid data set where the skin SSTs are from SLSTR. The subsurface temperatures are from the high resolution SST sensor on the trusted buoys, which is about 17 centimeters below the surface. And the fluxes and winds are from ECMWF ERA 5 reanalysis. At the time, I extracted all the trusted buoys about 40 degrees north. So most of the data is from the Arctic Ocean, which means that it's during the Arctic melt season. In other words, it's mostly daytime data. The nighttime data correspond to these these buoys, the Bay of Biscay, and for those lower latitude buoys, we see a perfect agreement with downline, but increased variability after 10 meters per second. For the daytime dependence, there's increased delta T with wind speed for all wind speeds. Because we have over 100,000 matchups, we can look at this in different ways, and this is the mean dependence for stratified by year and season. And it's easier to see that in all of these plots, the observed dependence gets away from downline at winds about 10 meters per second. So there's the downturn with increasing delta T for increasing winds. The seasonal plot I found interesting because it's saying that the trusted buoys, the dependence agree with downline from March to August, which is the top two plots. But from September to February, the dependence shifts down, same as with EPIC. So if I put all of them together, I just want to emphasize here two things. So these data sets are very, very different, but all of them have in common that have departures from downline, mainly at high winds, high heat fluxes, but also at low winds, low fluxes. They all have stratification with heat flux, which suggests that these departures are being driven by the heat flux. If I put just the mean dependence under one plot, all of them depart for at least 10 meters per second. So this 10 meter per second wind is emerging at this new wind speed threshold, after which we can have strong cooling under high winds. And if you think about it, this is counterintuitive because this is saying that there's thermal stratification at the surface that is maintained only by the heat fluxes in spite of the large vertical mixing associated with high winds. The other thing that it becomes clear here is that there's this shift up and down of the observed dependence with respect to downline. So quickly, I wanted to explore why the curve is shifting up and down, and I looked at the stratification of delta T versus wind for heat fluxes. So I took the data, I partitioned it in small ranges of heat flux, repeated the dependence, and we see two types of behavior emerging. On the left, we have IMOs and the trusted buoys, and you can see that as the flux range increases, delta T shifts, the dependence on delta T wind speed shifts down independently of the wind. There's two interesting aspects here. The only time we get good agreement with downline is for low winds and low heat fluxes. Below 100 watts per meter squared, the dependence shifts up. greater than 300 watts per meter square, the download dependence shifts down. With S-mode in EPIC, we saw a different behavior where the dependence shifts down, but to the right, depending on the wind, so it's not independent of the wind speed. Quickly, the delta T versus heat flux dependence, color-coded by wind speed in this case, all show linear dependence between delta T and the heat flux. So increasing delta T's for increasing fluxes. And if we put all of them together in under one plot, what I want to emphasize is that the slope of the linear dependence is pretty constant, or roughly constant, independent of the data set, independent of the year, independent of the season. So finally, the last comparison I made, I looked at the dependence of the delta T residual on heat flux. So this is what we are ignoring by using a simplified parameterization based on the wind speed alone. And as you can see, all the data sets suggest a linear dependence between the residual and the heat flux. The slopes are very, very similar. In fact, the slope for the buoys and IMOs is the same slope. And what this is saying is that if we have a change of 1/10 of a degree in the residual, this is equivalent to a change of roughly 150 watts per meter square in the heat flux. So in other words, if we want the cool skin to an accuracy of 1/10 of a degree, we need to include the heat fluxes, but we only need to know those heat fluxes up to 150 watts per meter square accuracy. And the fact that the trusted buoys and the IMOS crews gave the same result is just an indication that reanalysis fluxes now are accurate enough to be considered in this sort of application. So in conclusion, we have that these simplified parameterizations has helped us in the last 25 years with satellite SST validation, but we cannot keep ignoring the fact that the delta T has a strong dependence on heat flux. Conditions under which these heat flux dependence leads to significant departures from simplified models are lowering high heat fluxes, wind speeds greater than 10 meters per second, fronts the Arctic melt season. And if we want to improve delta T, we need to include the flux, but it seems that these 150 watts per meter square is perfectly doable nowadays from reanalysis. And that's all I have.
All right. Thank you, Sandra. Questions for her? Checking online too. Andy. Oh, Andrea, go ahead. You're up.
Hi, thanks for the talk. A quick question. Maybe I missed this information. The heat fluxes, where did you take the heat fluxes information from measurements or some data set? And if you try,
so
for example, ERA 5.
3 of the cruises, they were made packages, so the fluxes are from observations from the ship. And for the hybrid case, the fluxes were from reanalysis, ERA 5.
And with the observations, it was using the Core 3.6 model. So it was measured bulk parameters and using the Core 3.6.
So, do you consider ERA 5, it fluxes, the accuracy acceptable for
Yes.
correction?
So yeah, so that's the fact that I got same results for the IMAS cruises and the trusted buoys. At least they have sufficient accuracy to be included in a delta T physical model.
Andy was next. Yeah.
So have you considered putting viscosity in there as well?
Putting what? I'm sorry.
Viscosity.
It is there.
Well, at this point, it was just solely stratifying, just a simple stratification. It hasn't really gone to the stage of modeling of what might the next model step be.
Yeah, I have seen. I'm sure I've seen in like June of last year a really nice model that does a nice thing, but which you didn't show at all, which is a shame. But because it's yours. But yeah, viscosity would be the next obvious. Because it's so easy, it varies between about a factor 2 between 0 and 30. And
I just did preliminary comparisons with the core model, the Coolskin model, which includes heat flux in addition to wind speed, and the viscosity is there. And there are significant improvements for wind speed greater than 10 meters per second. I didn't show those.
Yeah, what I really meant was, the Donald model doesn't have viscosity in it.
Oh.
So I was just, it governs the thickness, you would think. I think it does, doesn't it? At least in the Saunders parameterization, governs the thickness of the laminar layer. So the other thing, I wasn't completely sure about daytime, because obviously you're thinking, is there a mixing in of diurnal warming versus, obviously it only really happens at low wind speeds, but the nighttime plots look really convincing. The daytime plots looked, I don't know. Well, I really like the nighttime plots, is what I'm saying.
Well, yeah, because Donald-Derived, his cool by is based on nighttime data only, because you need an approximation for the subskin and you want to remove any diurnal warming from your dependence. But what this is showing is that, yes, the dependence changes a little bit for daytime. You see the linear increase with between delta T and the wind. It's different dependence from the negative exponential of Donald, but you see the departure at 10 meters per second, even in that functional form. So you still at daytime see increasing delta T for increasing wind away from the Donald asymptote.
Do we have any idea what it is? What does your model do for that circumstance?
Yeah, this is all observations.
Oh, I know, but I'm just asking if your model handles it.
My gut feeling is it's the heat flux.
Yeah.
Why we haven't seen this before and why is it popping up in more and more data sets? I think it's a combination of factors. I think the radiometers and the fluxes are improving in quality, but it could be also physical. It could be that because of climate change, the heat fluxes and the winds are getting stronger and stronger, and this sort of behavior is becoming apparent. And maybe like Chris Merchant said the other day, they've noticed that cloud covering is decreasing worldwide. If you decrease the clouds, you increase the net heat flux, and maybe we're seeing a reflection of that. I don't know the answer, but it could be any of those things, or I don't know. For me, the one that gives validity to all of this is the repeatability of this departure of the Donald asymptote in so many different data sets. I think I saw it in Sang's Southern Buoy yesterday. So there was the downturn of the delta T at high winds in that data set too.
Okay. Let me shift to Salvatore and we can continue offline. Salvatore?
Yes, it's just a comment rather than a question about the ERA 5 fluxes. we made a regular measure of radiative fluxes over our mooring near Lampedusa, which is in open sea, and we found that radiative fluxes since 5 years every day, and we found that ERA5 fluxes work quite well, at least for the Mediterranean Sea. I cannot say this is true for the world ocean, but in the case of the sea, we found that there's a very good agreement. And also, when you run, for instance, simple one-dimensional model using ERA flux or direct measurement flux obtained in the mooring, they perform quite well, even very similar. So, at least for this case, ERA flux can be used with confidence.
Oh, great, thanks. No, it's positive encouragement. Prasenjit?
Okay, thanks. Very interesting talk, Sandra. Craig is not here, but it's not necessarily controversial, maybe just a logical next step. My question is very basic. You're showing delta T versus wind speed, and you're probably binning that at some interval, correct? Can you give a sense of the statistical significance, the sample size, especially where there is large departure? It was not there on the plot, but maybe you know.
I mean, the plots are very coherent. It's not like I'm seeing huge departures in the standard deviations from bin to bin. There are tons and tons of data, especially for IMOS and the trusted buoys. Each of those bins have hundreds of observations in the bin. So I did statistical significance test, but I'm sure there's so much data in there that I'm sure that's not an issue.
So you're sure that there is enough data that there's nothing wrong there in your interpretation?
I'm sorry?
There is enough data to make it statistically significant?
Yes, I think.
Okay. So what would be your politically correct conclusion here? Daniele's model is wrong or needs improvement?
I just think that we cannot apply it so loosely for all wind speeds. I think when we're starting to see these wind speeds greater than 10 meters per second more and more often, and that should be a moment to pause and try to look at the heat flux and wind speed dependence and try to improve the delta T models. I mean, it's time to move on from a constant bias, bias of 17/10 of a degree. That's all the model.
I think a quick cut, just building on that. What I'd say is in my words, going through it is, the Daniele model is a very useful assumption. It's something that was very useful when you're taking measurements on ships where you don't have quality winds, you don't have quality fluxes. You're matching conditions over the global ocean. It's a mean sort of fit. I think what we're saying here is we know, going back to the physics, there are other dependencies that factor in there. And if you have reliable enough information on those, then perhaps you can improve your answer in extreme conditions, in very high winds, very high fluxes. In the extreme conditions, if you have that information, you can potentially do a little bit better.
Yeah.
Okay, fair enough. All right, thanks, Sandra.
Okay, at this point, we're into the open discussion, so I just like to open it up to questions. First, to any additional questions to any of our speakers that you might have. Andy, did you have another one that you wanted to?
All I was really going to say at the end, this is something that we didn't really look at, but this is the core model, which I presume essentially means thereabouts the Fairall skin model, which is a blend of Saunders free and forced. Oh, you just concealed it. But it shows that the prediction is, hopefully these sorts of plots will revitalize actually doing the work. Although the effect beyond 10 meters a second is very interesting. I'm wondering if it's showing stuff that we probably didn't really expect. So I'd really like, it'd be great to get to the bottom of it. And I wonder if it's a sort of more fundamental science question that could be answered, funding bodies might be interested in actually exploring a fundamental science question like this, and rather than just pushing it off into what, oh, we already know about the skin effect sort of thing. So that's my hope, really. I'm not really asking a question. I'm just saying, hopefully we're going to rekindle this area, really.
What I was going to add to that, just in terms of potentially prompting other discussion going into the discussion period, is I think for me with a physicist background and that, I mean I really enjoyed the presentations in this session where we're looking at some of the physical things, we're seeing some of the potential value from physics. So a question that I would have to the community is a little bit is, are there other areas where it's worth spending some time on other questions like this that can help our answer? And so thinking of the ice temperature problem, the relationship of the ice temperature to the air temperature above. It seems like that's an area that we could do a little more. On this topic here, going into that, there's very active research in going from kind of core 3.6 to a core 4.0 model where there's an alternative. Instead of doing it solely on wind speed information, you can actually do some of the flux parameterization on wave information. And so are we at a point where we can bring in additional information on waves to help answer some of these questions? The flux world is looking at misaligned seas and going in that direction. So, I mean, are there any of those areas that are ripe for us as a community to start to build into some of these corrections? I mean, we're maybe just at the accuracy where we're adding flux onto wind speed, but can we look ahead? What else might we look at in 5 years' time, or what might we start that work on now? Any thoughts from the room on that? Any ideas? All right. Well, in terms of other questions, one that I had was kind of directed towards Daniele, and in following other presentations at Ocean Sciences, I'm aware of some of these new satellite missions being proposed that have elements for currents and various things on that. I was wondering, are those based on significantly different methods? Is there additional information in there? Would your work still be, something that could really add and contribute to those communities? Could we get to an even better answer?
Thanks, Gary, for this question. There are several options, actually, considering future current missions and future missions. I would like to have a follow-up of Jorge's question, and also Marwan comments even during yesterday's session about SWOT data. So SWOT is certainly something very helpful for the applications I showed today. The main, I would say, the main advantage and the fact that SWOT is going to be a game changer for this type of application is the type of observations which is native two-dimensional. So we don't need to interpolate anymore one-dimensional tracks to estimate dynamic topography. We already have two-dimensional images, which was before SWOT. This was just possible extracting information from additional tracers like we did for sea surface temperature and an ocean color. There are several techniques which can be implemented, and maybe here I'm going to advertise the work of some of my colleagues that are attending this meeting. I have in mind applications like the one presented by Claudia Fanelli. She has a poster on that. So there are several techniques based on convolutional neural networks that are very powerful to improve feature resolution. So this is something we would certainly account for in future applications to improve the feature resolution in sea surface temperature, but also to train neural network to learn features seen by SWOT data, for instance, like the two-dimensional features seen by SWOT. CMAR mission is also very interesting for us. We need to wait a bit more to have this data. The launch is foreseen in 2029, but the let's say observations from these new generation passive microwave radiometer with sea surface temperature, I would say all weather, around 10 to 15 kilometers resolution is also precious for these type of applications. For the estimate of SST within level 4 processing, we expect more consistency in terms of spatial gradients, and so benefits for this type of applications. And we are starting exploring this potential even in very simple numerical studies. So it's the turn of Mattia Sabatini, who has a poster on preliminary results on this topic. So we are trying to get prepared. I don't know to what extent we will be able to exploit information, especially in coastal areas, from future very high resolution SST observations. It's even more challenging considering the amount of noise which could be affecting these observations, but probably it is worth thinking about that as well.
Excellent. Thank you for that. Very interesting. So, other questions from anyone? The one I potentially had for Peter is, I'm trying to look, see if I still see, the mention was made of real-time data in that work, and I was just kind of curious, based on the nature of the comparisons, of kind of what would be a cutoff of a practical limit on that real time. I don't see. Okay, I'll follow up offline on that. All right. Any further questions? Any topics for discussion? Jana, anything? Thoughts from you?
Yeah, nothing in particular. It's kind of interesting to see how this diurnal warming discussion is still ongoing. Not very active, but that there is still some interest and work ongoing on that. So I'm looking forward to your next year's presentations in the GRIST meeting regarding developments, if any. But it's nice where it started from and where it's going.
Incremental, yeah, fits and starts.
Still?
The nature of research.
Better than nothing, right?
Yes, exactly. All right, well, we're coming, Veronica, did you? Yeah.
Didn't attend, but wondering what happened with the high latitude discussion.
So someone from the,
Yeah, so if you mean the task team, Veronica, yeah, so we had already a preliminary meeting during the morning coffee break where there were quite some people attending, around 12, I think, or 13. So that's a good number for a task team. And we've put down a few points. I don't know if there's going to be some time tomorrow to mention those, or Erica, maybe, yeah. Or else what can happen is that we will email the people attending the discussion with these points that we've put down and ask them to either keep on being interested, or if they're not interested anymore, just drop out of the mailing list. But if anybody who wasn't there in the morning discussion is interested to see what we've put down, then just talk to me now or Pia, or just email us and we can keep you in the loop. But it seems that I think the task team should be approved by the science team, but we are there with at least a few members and some fundamental in the first place, and then more advanced tasks to look at. And
excellent, yeah. Thanks.
Yep.
All right. Well, with that, we'll bring this session to a close. Thanks to all our speakers. Thanks for the discussion, the contributions from the field, and thanks to all. And I'll hand it back over to Erica, but I think there's some time on the session for posters. So.